folks, welcome to example 7. So now we're going to take a look at what we do when we have repeated irreducible quadratic factors. So much like when we had repeated linear factors, what we do is we just create fractions for each power of that irreducible quadratic factor. All right, so let's play this out. We're going to take a look at example 7. I'm going to scooch this up, and we're gonna figure out or try and discern why x squared minus 2x plus 3 is irreducible. All right, so if I take a look at x squared minus 2x plus 3, and you might think, oh, I can break that into two linear factors, right? And I would understand thinking that because you go x times x, 3 times 1, and you say, okay, if I want minus 2x, I'll put the minus 3 here and the plus 1 here. I've done it. But you always got to check that last. If I refoiled this, positive 1 times negative 3 is not positive 3, right? That's the main problem. And another way to kind of discern that this is irreducible is, again, if I look at the discriminant part, when I say discriminant, I mean the b squared minus 4ac, if I had run the quadratic formula, this is going to be all the stuff under the square root. So in this particular problem, it's negative 2 squared minus 4 times 1 times 3. If we play that out, we get negative 8. And anytime you have a negative discriminant, you're not going to have real solutions. And so there's no way it's going to break down into linear factors. All right, so I'm going to erase all this little my side quest here because I want to, well, actually, I'll leave it up there. I don't need to erase it. I'll start writing my fractions a little bit below here. So I have I have a quadratic factor that's squared. So ultimately, I do have an x to the 4th down here on the denominator. And I need to make sure, you always do want to check, like, hey, was the degree in the denominator higher than the degree in the numerator? And initially you might say, well, I had an x cubed over an x squared, and that's a problem, but it's really x squared squared. Okay, so if I take a look at this, I'm going to break this down into fractions. So I'm going to have x cubed minus 4x squared plus 9x minus 5 over x squared minus 2x plus 3 squared. I'm going to have a linear factor for 1 power of that denominator, right? 1 degree of that denominator. And then I'll have a second fraction, still a linear factor on the numerator, a linear expression on the numerator, over x squared minus 2x plus 3 squared, right? Same technique we would do for repeated linear factors. We're just repeating it now with quadratic factors. And again, anytime you've got a quadratic expression on the numerator, right, you go 1 less degree on the denominator. I'm sorry, I think I pointed wrong. When you have a quadratic expression on the denominator, you have a linear expression on the numerator. It's always 1 degree less, right? And just like when we had a linear expression on the denominator, then it was a constant up top. Degree 2 to degree 1, or if it's linear, degree 1 to degree 0. Okay, let's knock out these fractions. So my LCD is going to be x squared minus 2x plus 3 squared, okay? And I've gone through a good chunk of examples at this point, so I'm just going to talk about it at this point in that I'm going to multiply the LCD to this expression on the left, right? This expression on the right, this expression on the right. And when I do that, when I multiply this LCD to this entire fraction, the denominators are going to cancel out. So I'm ultimately going to have x cubed minus 4x squared plus 9x minus 5. When I multiply this expression to this denominator, right, I'm only going to cancel out 1 degree of it. So I'm going to have ax plus b times x squared minus 2x plus 3. And again, when I distribute this LCD or multiply this LCD to this term, the entire denominators cancel, and I'm left with just cx plus d, okay? All right, and so like always, you have a couple of options. You can multiply this out, line up cubic to cubic, quadratic to quadratic, linear to linear, constant to constant. Totally works. Or you could plug in values of x and see if you can get anything to, or not even see if you can get anything to cancel out, but you could solve that system, or you could solve for your 4 constants that way. I'm going to go ahead and I'm going to multiply everything out and line up terms. All right, so if I start to multiply everything out, x cubed minus 4x squared plus 9x minus 5. Okay, I got to distribute. So I got to take the ax, multiply it to every term, right? And then I got to take the b, multiply it to every term in that trinomial. And then I've got cx plus d. On the upside, I don't have to distribute anything here. So let me go one more level. I'm gonna write this out. So we're gonna have x cubed minus 4x squared plus 9x minus 5. All right, ax times x squared is ax cubed. Ax times negative 2x is negative 2ax squared. Ax times 3 is 3ax. All right, bx squared minus 2bx plus 3b plus cx plus d. Whew. All right, let's start lining these up. So I'm gonna go cubics. Cubed, cube, that's the only cube, right? So here I actually can get right away that a is 1. Okay, I've got one of my constants done. Let's look at the squared terms. I got negative 4x squared. Here's an x squared term. Here's an x squared term. All right, so if I take a look at that equation, I have negative 4 equaling negative 2a plus b. But the nice thing about that is I already know what a is equal to. So let me substitute that in. All right, so I'll have negative 4 equaling negative 2 plus b. Well, if I move the 2 over, that's going to just get me to b is negative 2. Okay, so this is going relatively quickly, in this case, lining them up. All right, let's take a look at linears. 9x, 3ax, negative 2bx, cx. All right, so let me put just a little separator. So I'm going to have a 9 here. That's going to be equal to 3a minus 2b plus c. But again, I know what a and b are, so let me substitute this in. So if I start to play this out, I have 9 is going to equal, okay, 3 times a. Well, if a is 1, that's the number 3. Minus 2 times b, so negative 2 times negative 2 would be positive 4 plus c. So I get a 7 over here. When I move that over, I'm getting that c is equal to 2. Okay? And that only leaves me 1 to go. Let's see what the constants are. So I'll box this one. Negative 5. I got a 3b and I've got a d. So I do have 2 terms over here. And let me just scooch this up because I think I'm going to run out of room. All right, and let me put some separators. So what did we have? Negative 5. I'll put this here. Negative 5, where the boxes is equal to 3b plus d. Okay, and b is negative 2, so negative 5 is equal to negative 6 plus d. When I move the 6 over, I'm going to get d equals 1. And that's actually where I can almost end my problem now, right? Because now I've solved it, and I'm saying this original expression is equal to, all right, a was 1, b was negative 2. So this would be x minus 2 on the numerator, x squared minus 2x plus 3, right? And then c was positive 2. So this would be 2x plus d is 1 over x squared minus 2x plus 3 squared. So let me just push this up a bit and let's write our end game answer. It's already here. I'm just going to write it up a little bit more properly. So therefore, I had my original fraction of x cubed minus 4x squared plus 9x minus 5 over x squared minus, minus 2x plus 3 squared. That was going to be equal to x minus 2 over x squared minus 2x plus 3, and then 2x plus 1 over x squared minus 2x plus 3 squared. Yeah. Now keep in mind, I did this with the solving systems of equations way. If you wanted to redo this by plugging in certain values of x, you're more than welcome to. Just looking at it, none of these factors have something that easily cancels. So I would definitely plug in x equaling 0. If I was trying this, I'd try x equaling 1, x equaling negative 1, and maybe x equaling 2. But you'd have to do it a good chunk of times because there was no obvious like x value to plug in that would zero out any of these factors. All right, thanks so much. Bye.